Welcome to the covalent chemical bond, a model. So we're going to talk about a model for covalent bonding. So why do chemical bonds occur? There's no principle of nature that states that bonds are favored or disfavored. There's no reason why, or there's nothing that says that, well, every atom will tend to form a chemical bond. It's all about energy. So bonds result from the tendency of the system to seek its lowest possible energy. So if the collection of atoms bonded in a molecule is more stable, which means lower in energy, than the separate atoms, then a chemical bond occurs. So if we give off energy by combining our atoms together into a molecule, then we say a bond occurs, we form a compound. If that doesn't happen, if we have to put in energy to get the compound to form, then in general, the chemical bond doesn't form. It will spontaneously decay if it does form. So let's look at the formation of methane from its elements in the gas phase. So methane is CH4, so we need one carbon atom for every 4 hydrogen atoms to give us methane, and this energy change is minus 1652 kilojoules per mole. That's quite a bit of energy. What this means is that we get out 1652 kilojoules of energy when we form methane from separated gaseous carbon and hydrogen atoms. Now, note that this is not hydrogen molecules, this is hydrogen atoms. So we've started out with all of our atoms totally separate. We get quite a bit of energy out by forming these bonds, which means that we should actually see methane. And we do. We see methane. Methane is significantly more stable than our atomic carbon and atomic hydrogen are. So 1 mole of methane molecules is more stable than 1 mole of carbon plus 4 moles of hydrogen atoms by 1652 kilojoules. So this means that methane is more stable relative to its separated atoms. We get energy out by forming these bonds, which means the bonds actually form. So it's useful to visualize these interactions between carbon and hydrogen as chemical bonds, but really it's just a force of attraction there. That force of attraction allows this energy to be released. That energy being released is what we call a bond. So there are 4 of these such bonds in methane, and thus the energy of each bond is the 1652 kilojoules per mole divided by 4, so 413 kilojoules per mole. So we say that each bond releases 413 kilojoules per mole of energy when we form it. So now let's look at another example. So methyl chloride, so CH3Cl. So this is basically the methane where we've pulled off 1 hydrogen and put on a chlorine instead. So the formation of gaseous methyl chloride from separated atoms is 1 mole of carbon atoms plus 3 mole of hydrogen atoms plus 1 mole of chlorine atoms gives us 1 mole of methyl chloride. Now, in this case, we get out 1578 kilojoules per mole of energy. And if we assume that the carbon-hydrogen bond energy is the same for methyl chloride as it was for methane, then we can calculate the bond energy for that chlorine-carbon bond. And we need 1 mole of carbon-chlorine bonds and 3 moles of carbon-hydrogen bonds, and we know that that gives us 1578 kilojoules per mole. And that means that the bond energy for the chlorine-carbon bond plus 3 times the bond energy for the carbon-hydrogen bond gives us 1578 kilojoules per mole. And we know that bond energy for the carbon-hydrogen bond is 413 kilojoules per mole. And so now we can figure out what that difference is. That means that the carbon-chlorine bond energy is equal to 1578 kilojoules per mole minus the 3 times 413, that's 1239 kilojoules per mole. Which means that the carbon-chlorine bond energy is 339 kilojoules per mole. So that means that forming a carbon-chlorine bond is less energetically favorable than forming a carbon-hydrogen bond, because we're getting out less energy. But it's important to note here that the concept of a bond is a human invention, right? There's no stick holding our 2 atoms together. It's just a useful method for us for dividing up the energy released. Right? It's a useful accounting tool for us, basically. It's a useful way of visualizing what's going on there. So is a useful method for dividing up the energy released when a stable molecule is formed from its component atoms. So in this way, a chemical bond represents a quantity of energy obtained from the overall molecular energy stabilization. But it's in an arbitrary way. We're sort of assuming that that bond energy has a certain value. And really, that's not strictly true, because the bond energy of any one bond depends on what else is bonded to the atoms in question. So we can't really just pull off one atom and stick on a different one and say, oh, well, those two bond energies are whatever values. We really have to look at the molecule as a whole, because that's going to change things some. So these models are human inventions that are based on an incomplete understanding of the way that nature or the universe works. And so a model doesn't fully equal reality. Right? It may be close, but it's always a simplification in some way. And so the chemical bond is just a model for us to think about how the energy changes occur as we move atoms around and connect them in different ways. Right? That connecting really just means they're near each other. Right? It doesn't mean that there's something physically connecting them together. So, but also remember, models are often wrong, which is, again, why it's not totally a representation of reality. So models are often based on speculation and always oversimplifications of how things really work. They tend to become more complicated with age, because as flaws are discovered, we tend to sort of patch them and try to add more detail to our model. But it's important to understand the assumptions inherent in the model before you use it to interpret observations or make predictions, because if you're trying to make a prediction that the model has not been designed to predict, it's going to fail, or will probably fail, and it may fail quite spectacularly. So if you know that the assumptions inherent in the model are not true, you probably shouldn't be using that model, unless you really have no other choice. But then you need to recognize that it's likely to fail. So simple models usually involve very restrictive assumptions. You're making a lot of assumptions about how simple the system is. And thus they can usually be used to make qualitative but not quantitative predictions. You may be able to say, oh, well, we should be able to release energy, but you might not have any idea how much energy can come out. Something like that. So let's look at something like the Aufbau principle. That works for most atoms, but not for something like chromium and copper. We fill in chromium and copper orbitals in a slightly different order than for most other atoms. But the Aufbau principle works fairly well. So this doesn't mean that just because there are some problems with the Aufbau principle that we should throw it away. It's useful for everything except chromium and copper. So it's pretty good, and it's not even that bad for chromium and copper. There are just a couple of exceptions there. So it is useful, but we need to be aware of its limitations. So it will fail to accurately predict the electron configurations for chromium and copper. So when a model is wrong, we often learn much more than when it's right. Because when it's wrong, that leads us to questions that we can then probe to try to patch our model. And when we patch the model, then we've learned a good bit. Because if our model is right, then we haven't really learned anything. We just know, okay, well, it works, and we can continue to apply it in this case. But in order to patch our model, we have to know why the model failed. And that means that asking those questions, probing why the model failed, allows us to go further and fix our model. So that was the covalent chemical bond, a model, therefore.